One of the biggest hurdles in astronomy was getting over the concept of geocentrism, a Earth-centered universe, and switching to a heliocentric model where the sun originally was the center of the universe. And now we understand that the sun's not the center of the universe, but the center of our solar system, which is one of a lot. And one of the big proponents for the heliocentric model is Nicholas Copernicus, an astronomer and religious philosopher from around the 15th, 16th century. And some things I want to make clear right now is that Copernicus did not come up with the idea of heliocentrism, but we associate heliocentrism with Copernicus, or as future astronomers sometimes refer to it as Copernicism. The reason that we associate the sun-centered model with Copernicus is because he backed up the idea with evidence. We'll see in future slides that he actually measured the distance to the planets using his models. So it's actually based off of a lot of geometry. Another fact to share about Copernicus was that while he was an astronomer and he was very much a supporter of a heliocentric model, he was too afraid to publish his ideas until posthumously after his death. He was afraid of what would happen, shame and embarrassment, so he waited until after he had passed away and he had his friends and family publish his work. Now, an idea that Copernicus was very much in favor of was this idea of uniform circular motion. All right, you've heard me say this a couple of times, but let's actually see a little demonstration of it. Right, a little ball on the string. Right, it can rotate around, and it'll give it a nice uniform circular motion. Right, shorten that up a little bit. So here's my ball, or my planet, orbiting in a uniform circular motion. It's going at a constant speed and a constant period. All right. Now, things to notice here. In my model, I have my planet, and I have the string providing a force. Copernicus didn't have an idea of forces. So there'll be a couple more years before we get to this idea of this action at a distance. This terrified philosophers, to be perfectly frank. How is it that a planet, without something physical holding it to an object, could cause it to orbit? So regardless, we'll step that question off to the side for now and come back to the planets orbiting. Copernicus was a huge fan of these uniform circular motion because, once again, universe was perfect. Universe was made by God in his worldview. So if it's going to be perfect, then it has to be perfect circles. So with that out of the way, let's move on. We're going to see how Copernicus was able to explain retrograde motion and start establishing how he backed up his ideas. Recall that in the geocentric model of the universe, we had to explain the retrograde motion, and that was the planets that do these crazy orbits, and they have epicycles. And when we switch to a heliocentric model, here's a lovely video to demonstrate what's happening. Let's go ahead and set this in motion. So what you're looking at here is sun at the center. Here's Earth doing its orbit around the sun. And then another planet. Let's call it Mars, for this example. So we'll have Mars doing its orbit around the sun. Now, to explain retrograde motion and those crazy epicycles, you just need to project from us, an observer here on Earth, out to Mars against the distant background stars. So this big outer circle, that's what we see on Earth, how the motion of the planet appears to us on Earth. Let's go ahead and set this in motion. Let's go ahead and slow this down. All right. So we see things pretty normal. The planet is orbiting in a westerly direction. But eventually, notice how Earth is gaining on Mars. It's about to surpass it. And look at the projection backwards. Look at the projection as Earth passes Mars. There's your retrograde motion. And back. So here's your epicycle from what we see here on Earth. Let's go ahead and let's play again. Everything looks fine. Everything looks fine. About to pass the planet. There's a retrograde. There it is again. One more time. Really settle this in. Here Earth comes up, passes the planet in orbit. Our view of the planet gets projected backwards relative to the stars. And get back to our nice normal orbits. So all retrograde motion is the consequence of two planets orbiting the same star. We live on one, and we are seeing what the other is. We're seeing what its motion is relative to the background stars. So there you have it. The retrograde motion of the planets is just due to the fact that Earth is orbiting the sun. We see a projection out to the planet. And when Earth surpasses it, we get that retrograde motion. All right, so let's start building up what Copernicus established. Copernicus showed, hey, not only are there the planets out there that we know of, but he could classify them into superior versus inferior planets. Pretty simple definitions. The inferior planets are just those that are closest to the sun, closer to the sun than Earth. Superior, the ones further away. So do not confuse inferior and superior to mean references to the size of the planets. It's just a comment on how close relative to the sun they are. So Mercury and Venus would be the inferior planets, Mars, Jupiter, Saturn, Neptune, the superior planets. Now, how did Copernicus actually make his insight to establish the distances to the planets? It's basically a geometry problem that you can measure here on Earth. So let's see what he did. So here we're going to look at an example of an inferior planet. The geometry is similar for a superior planet, so don't worry about that. We'll have the inferior planets orbiting around the sun and Earth's orbit outside. All right. Now let's start defining some crucial points here. Specifically, these points here are going to be matters, but we need to get a map here. Here's our superior conjunction. All right. Now the point of conjunctions is that these are points you can easily measure. So what does a conjunction point mean? How can you know that you're at a conjunction? If we were to look at this bird's eye view down the solar system, you would see a conjunction point is Earth, Sun, planet. All right. So how can we, while sitting on Earth, know we're at a conjunction? Well, it refers to objects in their right ascension in the skies. Remember, there are points on the celestial sphere. How far is their right ascension? Here's a wonderful example of, say, Mercury and Venus being in conjunction right now. They're at the same right ascension. So these are points that you can measure in the sky. You can say when things are in conjunction easily here on Earth. So coming back, let's start filling in all these points. Here's our superior conjunction. Come around. There's an inferior conjunction. Not the same thing as the superior and inferior planets. This just refers to the distance that is closest between the planet and Earth, inferior conjunction, and the superior distance furthest between the planet and Earth when we're on opposite sides of the sun. All right, last two. The greatest western elongation and the greatest eastern elongation. All right, we can use either one of these to finish our problem. I'll focus on the eastern elongation, but the way you find these is you look at the night sky. Let's go back a bit. Look at the night sky and see, well, at what time in the year is this planet furthest west or furthest east in the night sky? When it's at that point, you know you're at one of these elongation points. So now we've set up a geometry problem, all right? Here's our triangle. If I go from Earth to the, in this case, inferior planet, here is the distance between the inferior planet and the sun, and here's a number that's going to be very important to us. It's a astronomical unit, the distance between Earth and the sun. All right? So let's highlight this triangle that we're going to focus on. And there it is. The radius between the inferior planet and the sun and 1 astronomical unit. So, exploiting this geometry, cut out all the stuff, cut out all the other elongations and conjunction points. Here's what matters. When this, in the picture we're using, once again, this is the eastern elongation that we're using. Let's go forward again. Using the eastern elongation, you look at the night sky and you say, hey, what angle, how far east is that inferior planet? This, by definition from the geometry, has to be a right angle. So we've set up a triangle. Right? The astronomical unit, the distance between Earth and the sun, will be your hypotenuse. And we have these side lengths, the distance between the Earth and planet. We don't particularly care about that right now. Copernicus just wanted to measure the size of the solar system. He wanted to know the order of the planets by measuring their distances, their radius from the sun. So that's our radius inferior planet. Well, if you remember your sine and cosine relationships, the radius of the inferior planet will just be the hypotenuse, 1 astronomical unit, times the sine of the angle. So, here on Earth, we measure these angles. We measure these theta points. Say, what is, in this picture, the greatest eastern elongation? Once I know that angle, I can calculate the distance to that planet. Now, Copernicus didn't know actually what an astronomical unit is. In fact, he had to just define it. He said, my measuring stick will be the distance between Earth and the sun. And if I know that value, I know the distances to the planets. Our modern value, we know 1 AU to be, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So about 1.5 times 10 to the 11th meters. Whew. Now that out of the way, let's talk about the values that Copernicus found. Copernicus, and this is why we associate heliocentrism, he measured the distances to the planets. He showed that Mercury was 0.38 AU away from the sun. Our modern values, 0.39. And all he needed was the angles in the skies. Keep going. He nailed Venus almost perfectly. Earth's a scratch. That's just the definition. Mars. He showed that Mars was 1.52 astronomical units away from the sun, and that's almost dead on to what our modern values are. The worst he did was Saturn, and that goes to the further away the planet is, the smaller the angle at those elongation points are going to be, and the smaller the angle, the greater your uncertainty, the greater your error. But still, he was in the right ballpark. 9 AU, 9.58 AU. So Copernicus was able to measure the distances to the planets.